So yeah, it's my great honor to introduce Michael, and he's a DeepMind professor of AI at the University of Oxford, and he was previously the head of graph learning research team at Twitter, and he was also professor at the ICL Imperial College London, and hold many visiting positions. And he's a leading figure in the field of geometric deep learning, and he's also very successful serial entrepreneur with a lot of startups. Without further ado, let's welcome Michael. Thank you.
It's actually my first time on this campus, so it's great pleasure to be. So I will more or less repeat the talk that I gave yesterday to my so you get the taste for free without paying whatever outrageous registration fees they charge. So I would like to talk about, well, a little bit about geometric deep learning, right? It's probably more general principle of ML, but then mostly focus on some recent works that we've been doing on graph neural networks, and in particular physics-inspired approaches. So they allow you to derive GNN architectures, derive and analyze them using ideas from physics, from differential equations. Well, there are several people sitting here with pioneering contributions to this more specifically. So first of all, well, I think I probably have the best position in the world because it gives me this unique opportunity to harass Google every time at machine learning conferences. So I have the DeepMind chair, so I asked them to show me the chair, and they failed to give me a chair. Only stools were available. Probably obviously not good enough, but that's what Google now has. So seriously speaking, let me start maybe with some historical excursion. I would like to start with this quote. It's a bit poetic, but I think it's beautiful. So this is Weil, one of the most important mathematicians in physics, who spoke very poetically about the concept of symmetry. Right? So that's why this narrow is defined as spinning. It's one idea by which men through the ages try to comprehend and create order, beauty, and perfection. And, symmetry itself is a Greek word, so it goes back to ancient Greeks. And Plato, for example, believed that symmetric polyhedra, what nowadays we call platonic solids, because they are so perfect, they must be the basic building blocks of the universe. It's not such a crazy idea. That's how crystals are organized. Even nowadays, these ideas are still valid. And the Greeks are also credited with creating geometry that we probably still teach at school as D-geometry, right? Euclidean geometry, that, as you know, is based on 5 axioms or 5 postulates. And one of them, the fifth one, about the parallel lines, stood out. Something that many illustrious mathematicians tried to prove centuries to no avail until the 19th century. In the 19th century came the realization that we can actually construct self-consistent geometries that do not satisfy the parallels postulate of Euclidean geometry, and this gave rise to different types of geometries. Also gave even the non-Euclidean, and it created this unhealthy zoo of different constructions that it was not even clear how they are related to each other and what constitutes a valid definition of geometry. And it required a brilliant insight of a young genius mathematician called Felix Klein. He was only 23 years old in 1872 when he got an appointment as full professor at the University of Erlangen in Germany. And as it was customary, and probably still customary in Germany nowadays, he was asked to deliver an inaugural lecture about his future research, which actually never happened. So neither the lecture, so he talked about mathematical education, nor his stay at Erlangen. He moved very quickly to a different place, which is Göttingen, which was the place of mathematics at that time. But he did publish a little booklet, and this is what entered the history of mathematics as the Erlangen program. And there he described a radically different approach to geometry, essentially regarding geometry as space plus some group of transformations, looking at how different geometric objects are affected by the action of some transformation group. Right? So he could show that Euclidean geometry arises from the Euclidean group of transformations, so rotations, translations, and reflections. And they can take bigger groups like projective group or affine group, and it gives different quantities that are preserved or not preserved. And this really had a transformational impact on geometry and mathematics in general, but probably the biggest impact it had in the 20th century was on physics, where about 100 years ago, and slightly earlier, came the realization that we can derive the very fundamental laws of the universe from considerations of symmetry, right? So that's the first principle from which you can derive things that before that were considered empirical, like conservation of energy. So it comes from the symmetry of time. And that was a remarkable insight of René Neutra. And in some incarnation, this is what nowadays we know as the standard model in particle physics, right? So you can derive all physics from group theory, right? So these are the different groups that we see. So physicists call external symmetries, right? So one kind group that gives rise to Minkowski geometry of space-time, or internal symmetries. So these are different symmetries from which different forces or interactions arise. And I think it was beautifully formulated very laconically to the point by Philip Anderson, Nobel laureate in physics, that it's only overstating, slightly overstating to say that physics is the study of symmetry. Now, what does it all have to do with deep learning? So, first of all, the situation we have is a little bit similar to what happened in geometry in the 19th century. We have a lot of different architectures. So, these zoo of neural networks, like convolutional neural networks, recurrent neural networks, so they are all derived historically in different contexts to deal with different types of data, to deal with different types of problems. CNNs, for example, come from image analysis, recurrent neural networks from time series analysis, and apparently there is no common denominator between them. So, geometric deep learning is this concept that in the spirit of the elegant program of Klein tries to use a common denominator, basically derive these architectures from first principles, and also serve as a blueprint that allows you not only to understand teach the existing architectures, but also create new ones. And if you think of at least a simple setting of supervised ML, some people cynically say that deep learning is just glorified curve fitting, which is probably to some extent true, right? And you can think of this classical example of classification of cats and dogs as some kind of function interpolation, right? So I give you examples of cats and dogs, right? So these are high-dimensional inputs, and I have some function that I sample, right? So that's my classifier produces binary output, but it's a cat or a dog. And then from these samples, I would like to interpolate previously unseen examples. So the question is what we put in this black box, and historically these have been neural networks, right? Since the first models appeared, like the perceptron that was published by Rosenblatt in the late 50s. We know, of course, that this simple neural network is not good enough, right? So it cannot even represent a simple function like XOR. And this was argued in the famous or infamous book, Perceptrons by Minsky and Liebert. But we also know that if we just take two layers of such perceptrons, we get a property that we call universal approximation, right? So these neural networks are sufficiently generic that they can represent any continuous function to any desired degree of accuracy. But this is a kind of existence result, right? So it doesn't tell you exactly how many neurons we need, how to find these parameters, in fact. And if you ask the question, how many samples do you need to represent the function, then but the problem is not well defined, right? Because there can be infinitely many continuous functions that can pass through this point. So you need to make some extra assumptions about these functions, which involves some knowledge of regularity that mathematicians are very familiar with. So if you take even a very well-studied class of regularity like Lipschitz continuous functions, you see that the bounds on the number of points do not scale well with dimension. So it's a manifestation of this geometric or statistical phenomena that we call the curse of dimensionality. And the bottom line is that the number of samples will be probably more than the number of not only cats and dogs on Earth, but particles in the universe by far, right? So it scales exponentially with dimension. And this is not something that is really practical. So the idea is that the idea of geometric deep learning is that you shouldn't treat cats and dogs or other inputs as just high-dimensional vectors. So in this case, there are images that live on some low-dimensional domain, right? So they're signals defined on a grid, and we can basically we can model it as such. So we have a domain, right? In this case, it's a grid or a plane on which we can define signals, right? These are images, and on the domain we can act with some symmetry, right? So, for example, the group of translations that moves points in the plane. The action of this group through some group representation, right? Shift operator in this case. Can be applied to the signals of the domain, and now we have functions that take as input these signals. We can design these functions, right, by baking some properties into the neural network architecture that respects this symmetry, right? For example, in the form of invariants. So invariance again historically appeared quite early, already in the probably 60s or 70s in computer vision and pattern recognition problems. So if you want to classify an object in an image as a cat, you don't care where this object is located. Right? So it appeared, for example, in optical character recognition. So I want to be able to say that for any application of the group element on my input, the output of the function will be the same, right? And this famous book Perceptrons by Minsky and Papert, it was not only criticizing perceptrons, it was actually, at least to my knowledge, the first geometric take on machine learning. The subtitle was actually computational geometry, which is a term that they invented. The first realizations of these kind of architectures that incorporate these priors, the first inspiration came from work in neuroscience, famous work that brought Hubel and Wiesel the Nobel Prize in Medicine in the 80s on the organization of the visual cortex. And their conclusion was that in human brain, right, or brain of mammals, the neurons are organized locally, so they so-called receptive fields, and the weights or the parameters of these neural networks are shared. So this gave rise to the first architectures that implemented these ideas. First, the neocognitron of Fukushima, and then, of course, the classical convolutional neural networks by Jan LeCun. And you can see that this is a particular case of this geometric deep learning blueprint. So we have, in this case, a plane or a grid. The symmetry group is translations. We have images that live on this grid, and the group acts on images through the translation operator, right? And the functions that respect these symmetries, or that are equivariant with respect to symmetries, right, or commute with the shift, are convolutions. This is actually how you can define convolution, or I think how you should define convolution as a linear operator that commutes with shift. So convolution arises as the only linear equivariant operator with respect to this group of symmetry. Right? So it's not just some arbitrary definition. And also the Fourier transform, right, which diagonalizes these operations. So today we'll be talking about graph neural networks. So graph neural networks is another instance of this geometric deep learning blueprint. In this case, the group of symmetries is the group of node permutations, because in graphs, unless you provide some extra information, we don't have a way to canonically order the nodes, right? So the graph is just topological structure, right? So I tell you how the nodes are connected, but I don't have a special way to say that this is node number 1 or this is node number 2, right? So this is totally arbitrary. So the signal in this case are node features, and the functions that act on the graph, implemented in the form of message passing that we'll be discussing shortly, respect this symmetry, right? So they're equivariant with respect to permutations. Now, I'm often asked whether this geometric deep learning blueprints produces really anything new, right? So of course it's nice to be able to explain CNNs, right, that are already probably evolved at least 50 years, but is there something new that comes out of it? And I think indeed one successful example are these geometric or equivariant GNNs or transformers, and they probably appeared around 5 years ago. This became popular, and they are nowadays very widely used in chemistry. So the idea here is that if you have graphs where the what we call geometric graphs, right? So some of the node features also have geometric quantities. For example, think of a molecule represented as a graph, right? So the nodes will represent atoms, and the edges represent chemical bonds. And the atoms have scalar type of features, like the type of the atom, right? But also geometric type of features, such as the positions of the atoms, or maybe forces that different atoms exert on each other. So these geometric components can also transform in their own way by some continuous group of transformations. For example, the special orthogonal group, right? So I can take my molecule and rotate and translate it in space, right? And in this case, we have two types of symmetry. So we have the symmetry of the domain, right, which is the ordering of the atoms in the molecule, right, permutation of the nodes in the graph, and also the data symmetry, right, which is the transformations, rotations and translations of, for example, the positions of the atoms. And now we need functions that will be respecting both symmetries in the form of equivariance with respect to both matrices. And as you probably know, this has been very successfully used for protein structure prediction, the famous protein folding problem. So in 21, in August, two papers appeared at the same time on the covers of Nature and Science. One is DeepMind's AlphaFold. They used invariant point attention, which is the invariant transformer, and a parallel work from the group of David Baker at the University of Washington, Rosetta Fold, which is SE3 equivariant transformer as well. And nowadays, of course, everyone is obsessed with generative ML, right? So same way as you can generate images with DALI or Mid-Journey, fusion models, flow matching models. You can also generate molecules. So this is an animation from our own paper. So here we can generate a molecule that is constrained by the geometry of a protein model. So this is how you design drugs, right? So you have some target. So it's typically a protein. It has some kind of pocket-like structure, and that's where you want your drug molecule to bind, right? So it needs to be geometrically and chemically complementary, and we can diffuse in some space of these molecules the right candidate. And this is also an equivariant architecture, right? So it's an equivariant diffusion model, and we also have that's favorite here, and equivariant flow matching for protein backbone gene. So we design new proteins, and proteins can also be used as a drug candidate, so it's called biological drugs. Now, this is obviously a very broad idea, right? So the geometric deep learning blueprint, you can apply it to more or less any type of geometric structure with a corresponding group. So typically, of course, to be able to implement it, we want it to be low dimensional, discrete, small number of small group size. But more or less anything that is used nowadays in deep learning can be explained from the perspective of this blueprint. Whether it's CNNs, whether it's LSTMs, for example, or deep sets or transformers, graph neural networks, some more exotic architectures, like mesh convolutional. And so, in a sense, it's a kind of universal blueprint. People are familiar with this. It's wonderful. I'm not saying that this is a kind of panacea, but I think it's a valid viewpoint. So I would like to talk more in details about graphs, and I think for many people here, I don't need to convince you that graphs are very. Yeah, question.
What is GAUGE? G-A-U-G?
Sorry.
One. Yeah.
Oh, the gauges. So yeah, so gauges. Well, I will try to answer briefly. So on manifolds, right? When you want to do deep learning on manifolds, you want to do something similar to convolutional networks. The problem when you work on manifolds that you don't have a global reference frame, right? So what is called a gauge is the choice of a local reference frame at every point on the manifold, right? In the corresponding tangent spaces. So if it's very smoothly on the manifold, this is called the gauge. And because I have this ambiguity, right? So on an orientable Riemannian manifold, this is defined after rotation, after special orthogonal group. So you want the choice of the filter to be equivariant with respect to the choice. So that was the line of work from Taco Coin and Max Pelling. So this is what. This is the term used in physics. Okay, so mathematics is called structure of the bundle. So basically, graphs can be used to model more or less anything from very little things like molecules to very large things like social networks. So any system of relations and interactions can be abstracted as a graph. And graph neural networks are just parametric functions that take as input a graph with some features and produce some output. So the output can be different, the input can be different. One of the classical examples is virtual drug screening. So I give you a molecule and I want to predict some properties. So for example, its toxicity or whether it can be dissolved in water or its binding energy. This is a very common and very important problem when you try to design new drugs. So the way that graph neural networks work, or at least the majority of graph neural networks that are used in practice, is by what's called message passing. So every node is connected to its neighbors, and you use the information from your neighbors to send messages to the target node, right? So every node receives information from its neighbors, right? And you do it multiple times, right? So every layer has this kind of information exchange layer. Now, because you don't have a canonical order of the nodes in the graph, any permutation is valid, right? So you need to aggregate this information in a way that is insensitive to the order. In other words, you need to use a permutation invariant aggregation function, sample, maximum, average, something like this. And different types of neural network, graph neural network architectures differ in the way that these message passing and aggregation functions are chosen. Right? So in general, message passing, this is just a bivariate function. You can also design attentional architectures where it has this particular structure. And then convolutional architectures, the aggregation is done by on some transformed features that are aggregated with coefficients that depend only on the structure of the graph, not the features themselves. if you write it as matrix equations, X here denotes the node features arranged as rows of the matrix. Then in convolutional architectures, the propagation, right, the propagation of information between nodes is done by a matrix that is independent on this, right? So it's only dependent on the structure of the graph. It's some normalized adjacency matrix of the graph. In attentional, it's a matrix valued function, so it's still linear aggregation, but it depends on X. And in general message passing, it's some non-linear. So what do we know about the class of functions that we can implement using message passing? So there is this theoretical result that establishes under some technical conditions that if I choose the aggregation operator at message passing, in particular they need to be injective, the upper bound on the expressive power of message passing is the Weisfeiler-Lehman graph isomorphism test. And it's a classical algorithm in graph theory that was invented in the late 60s by Lehman and Weisfeiler with the goal of testing whether two graphs are structurally similar. So it's actually interesting that the problem came from chemoinformatics. So I worked with a guy called Georg Vladutz, who was a chemist, and he asked them, can we do search data sets of molecules? And to do it, basically they represented molecules as graphs, and they tried to see whether graphs are structurally similar. Right? So isomorphism means that we have node-wise edge preserving by ejection. Right? So I can basically the graphs are the same up to renumbering the nodes. Right? So you can see that these graphs, for example, are not isomorphic because one has 6 cycles and another one has 5 cycles. Right? But if you look at these graphs, basically you need some computational way of determining it. So what Weisfeiler-Lehman test does, it examines the structure of the neighborhood of every node. And you see that initially in this graph, we have 2 types of nodes, right? So we have nodes with 2 neighbors and nodes with 3 neighbors. Right? So if I apply some injective function to these neighborhoods, I can assign them different labels, right, or different colors. So I can distinguish between these different nodes. So this will be the new coloring of this graph. I can repeat this process again, right? So now I have 3 types of different neighborhoods, and this will correspond to 3 different labels. But at some point, the colors will stop changing, at which point I can output the distribution. And the algorithm is designed in a way that if the distributions are different, I can proclaim that the graphs are not isomorphic. But if the distributions are the same, I actually don't know. Right? So in this case, the graphs are not isomorphic, but they cannot be distinguished by the WL test. Or in other words, it's a necessary but insufficient condition for establishing graph isomorphism. So this is what we know in theory, right? So in theory, it's nice, of course, that there is one-to-one correspondence between message passing neural networks and the WL test. So it allows us to talk about expressive power of graph neural networks. In practice, we see that some graphs that are not isomorphic cannot be tested, but also a practical computational problem is if I have a graph that looks like this, it might be not friendly for message passing, right? So if I'm sending information from this block to this block, all this information has to go through this single connection. Information might get lost on the way from one side of the graph to the other. So on the theoretical side, what exists it's an entire hierarchy of WL tests that are progressively more expressive, right? And of course, always some classes of graphs that cannot be distinguished. And there has been a line of works that try to come up with the corresponding neural network architectures that will be upper bounded by KW. KGNNs, the work of Kagai Maron and Christopher Morris. On the practical side, what is common to do is to decouple the input graph from the computational graph. So you're given the graph as an input, but you do propagation on some other graph. And this is known under the umbrella term of graph inquiry. Again, there is a slew of different works that try to do this for different considerations. But what happens is that we have a gap between theory and practice, right? Because Weisfeiler-Lehman requires us to use the input graph to propagate information. What we do in practice, and sometimes just for computational reasons, if you have a very large graph like a social network, some nodes might have millions of neighbors, it's totally impossible computationally to use information from all of them, right? So you subsample the neighborhoods, and as a result, you're de facto are not using the input graph to propagate information. So in classical GNNs, you use the input graph to propagate information, and you can equip the graph with more structure, right? So you can, for example, add positional encoding. So this is what is used in transformers in NLP, right? Because in NLP, the order of words in a sentence is important. So these are not necessarily permutation invariant functions. You can lift the graph to higher dimensional topological spaces like spatial or cellular complexes. You can consider the graph as a collection of subgraphs that are extracted from the graph with some policy, right? This way you can do some kind of coordinated message passing on these subgraphs, and this allows you to be probably more expressive than WL test. But I also mentioned equivariant GNNs for also some continuous symmetry of the data, or maybe special cases like regular graphs that have grid-like structure. And in this case, you can get convolutional neural network as a special form of message passing. So the common denominator of these methods is when you use more structure. The other extreme will be to use less structure, and you can say that for some reasons you don't like the graph that you're given, so you can completely disregard it, right? So I'm now looking at the set of node features, and again, they inherit the permutation symmetry of the graph. And there are methods like deep sets or point nets that work with sets, right? So that's the basic object for inputting. And these methods are used, for example, in computer graphics and vision applications to analyze point clouds. The other extreme is to allow interaction between any pair of nodes, and this is how transformers work, right? So transformers essentially assume that you have a complete graph, right? That it's fully connected, every node is connected with every other node, and you try to learn the graph that is optimal for your task, for example, through the attention mechanism, right? So it's a kind of latent structure learning. And graph rewiring sits somewhere in the middle. So you do want to use your graph, right? So we can call it the local bias, but you also want to be more flexible to allow the graph to be more efficient for message passing. And so basically, it's a combination of these two extremes. Now, if we also compare graphs to other domains that are typically encountered with this geometric deep learning zoo, let's say we look at graphs and we look at grids, right, which are a special case of graphs, and we also look at meshes, which are graphs with some extra structure, right? So these are simplicial complexes. We have nodes, we have edges, and we also have triangles. So one thing that we notice is that the way that we aggregate information from neighbors is very different. So on the grids, I have canonical order of my neighbors, right? So I can designate, for example, the top neighbor to be number one, right? And order them in a canonical way, so there is no ambiguity in which neighbor is which, right? So that's how I can define convolution, so I can distinguish between different nodes and give them special coefficients on their own. On the mesh, I can designate my first neighbor and then order the rest of the neighbors, for example, in clockwise orientation. But the choice of the first neighbor is defined up to rotation, right? So it's up to cyclic rotation. So that's exactly the gauge symmetry that you asked before, right? So that's exactly this local rotation that we do. In graphs, as we've seen, any permutation will do, right? So in a sense, graphs have the least structure of all these objects. Now, another thing that you'll notice is that I can think of meshes as discretization of continuous surfaces, right? Or I can think of grids as discretization of the plane, maybe more general homogeneous spaces. We don't have this immediate analogy for graphs, even though there is an entire field of network geometry, but it would be cool to have continuous models for geometries, right? The graph will, and the layers will come as some discretization of some continuous object. And that's exactly what I would like to talk about today, which is physics-inspired graph dynamics. And the metaphor I would like to have in mind for the rest of this talk is a dynamic system, right? So every node is a particle that lives in a high-dimensional space, and it follows some trajectory that is shown here by these red lines. The behavior of these particles is governed by some system of differential equations. It's written here, right? So I can arrange the coordinates as a matrix, right? Every row here is a position of a particle, and it also has time. And this mindset has been explored quite a while, right? In learning, so that cover, for example, some pioneering work on neural ODEs, and also on some instances of these kind of models for graphs. So if you discretize the time here, for example, with constant time step, this would correspond to layers of the graph. Now, what is a graph is a way of coupling the different behavior of different particles. So basically, the trajectories do not exist on their own. The behavior of one particle depends on other particles. In which way? Through the graph, right? So particles that are connected by edges interact. We'll see that in some situations we can also think of the graph as a discretization of some continuous space. But that's the model. Now, first question you can ask: what kind of equations can we use here? Right? So we have more or less anything, any physical model. So, but probably the first thing that the simplest approach that comes to your mind would be when you think of propagation or diffusion of information in some domain to think of diffusion equation, right? And this is one of the processes in physics that has been studied mathematically, probably for the first time many centuries ago, by none less than Sir Isaac Newton himself, an anonymous paper published in the Transactions of the Royal Society in 1701. So he wrote it in Latin. He described an experiment and a thermometer that he built, and a mathematical model that describes how hot bodies lose their temperature, right? So he would measure the temperature. He called it heat at that time, which was not correct term in modern terminology. And basically, he described what nowadays we call the Newton law of cooling, which tells us that the temperature a hot body loses in a given time is proportional to the temperature difference between the object and the environment. Now, this is a very general rule, and you can apply it to any quantity. So you can talk about a chemical diffusion or even diffusion of rumors on a social network, right? So let's see how this Newton law of cooling is implemented on the graph. So we have a graph where every node has some features, right? So think of it as temperature. So what we have here is the self-temperature at the node I, right? We have the temperature of the environment, which is the average of the temperature of the neighbors, right? And the rate of temperature change is the temporal data, right? So here is local discrete version of Newton's law of cooling on the graph. Now allow me to rearrange slightly this right-hand side, and I can write it like this. So what you see here in parentheses, right? So this is the difference of endpoints of an edge. This is the discrete analogy of the gradient equation, right? So what is a gradient on the graph? It takes a signal that lives on the nodes and makes it into a signal that lives on the edges, right? So it's an analogy of scalar and vector fields on the edges, right? Now we can do the opposite. Now we have some stuff that lives on the edges. We can look at all the edges that emanate from a node and aggregate, just to take a sum of this field on these edges. And this is the analogy of the adjoint to the gradient, what we call the divergence operator in classical calculus, right? So together, the divergence of the gradient or minus divergence of the gradient, depending on the notation, gives us what we call the Laplacian operation. So Laplacian measures how different you are from your neighbors. And it's a very important operator that arises more or less anywhere in equations of mathematical physics. And what is written here is the simplest form of diffusion equation that is homogeneous and is right? So the change of temperature depends on how different you are from your environment, right? So this is a differential version of the Newton law of cooling, right? Now the Laplacian will typically be a sparse matrix on a graph. It has the same structure as the adjacency matrix, and this system of equations sometimes can be solved in closed form. Now, what is also interesting about the heat equation is that it's a prototypical example of a gradient flow. So a gradient flow is a variational version of simplest descent. So it's an evolution equation that looks like you take a step in the negative gradient direction of some energy, right, denoted here by calligraphic E. And the energy that corresponds to the heat equation is what we call the Dirichlet energy, right? So it tells us how different you are from your neighbors, right? So it's the norm of the gradient squared on the edges of the graph, right? And the smallest value you can get here is 0 when your neighbors are exactly equal to yourself. So what we can show that basically it's kind of smoothness of the node features, right? How different you are from your neighbors, and it decreases along the flow. So as we run the diffusion, the features will become smoother and smoother, and in the limit, the Dirichlet energy will be 0, right? So all the features on the graph will be constant, and this is a phenomenon that is called oversmoothing. So it's considered undesirable at graph neural networks, but it's not necessarily a malignant phenomenon. So you can do without any learning if you have a transductive setting, right? So if I know the labels of a few nodes in the graph, I can use them as boundary condition, and I can diffuse these labels on the graph, right? And, under the assumption of what is called homophily. Homophily means that my neighbors are similar to myself. This actually works extremely well. If the graph is not homophilic, then of course this is not good. We need to do something more interesting, more sophisticated. So back to this metaphor, the classical approach to the design of GNNs, you start with some, well, you can think of it as a physical model. You discretize it and you parameterize the evolution equations, right? So each step of your iterative solution, right, or each iteration of your solver will correspond to a layer of graph neural network, so you just parameterize it. You make these parameters known. So what I hope to convince you that there is a better approach, and the approach is to start with an energy, parameterize the energy. And then you derive the evolution equation as the gradient flow of this energy. And what it gives you, of course, it restricts your architectural space, right? Because not every evolution equation is necessarily gradient flow, but what it gives you in exchange is better interpretability. right? And of course, interpretability is a little bit kind of charged word in machine learning. What I mean by this is would be able to mathematically guarantee that certain things happen or not happen. Right? Let me give you an example. So this is a toy example of a graph where the colors of the nodes represent labels, right? So this is a perfect example of heterophilic graph, right? So every blue node has only red neighbors and vice versa. And the two-dimensional coordinates represent some feature space, right? So again, for example, two-dimensional features. So what I want to do here is to do node classification. So I want to be able to distinguish between the reds and the blues. And I can show you this process, right? So these are the trajectories of the evolution that completely separate the reds and the blues, right? Now, how we do it? So in this case, we have a parametric version of the direction energy. Let's see. How to move it, but basically what is written here is an inner product of xi with wxj, right? So the gradient flow, the evolution equation looks like this. So W is what is called the channel mixing matrix, right? So if you look at this evolution, what you do is at every node of the graph, you transform by the matrix W features, right? So that's the right-hand multiplication. I remind you the features live in the rows of this matrix, right? So W is shared across the nodes. So this is a transformation in the feature space. And A is the diffusion operation, right? So that's how you interact between different nodes along the edges of the graph. So this is what we call a convolutional architecture, right? Because the way that the nodes interact is independent on X, right? So it's fixed, it depends on the structure of the graph. And what happens here is that we have different directions in the feature space along the positive eigenvectors of W. We have attractive interactions, right? So nodes become closer. This corresponds to this vertical direction in this spot. And along the negative eigenvectors of W, we have repulsion, right? So the nodes drift apart. And what we can prove is that under some technical conditions, right, assumptions in this case, the matrix W must be symmetric. So this is a gradient flow, and it must have sufficiently large negative eigenvalues. We can prove that this simple linear diffusion, right, or convolutional GNN, can probably avoid oversmoothing. So oversmoothing would mean that all the points in the limit collapse into a single point, right, which is not desirable, right? So it means that we will not be able to separate the nodes. In this case, we can do it, and this kind of contradicts the folklore that I often see in GraphML literature that says that because this looks like a low-pass filter, right? So basically this matrix averages your neighbors on a heterophilic graph, it will not, right? Because it will mix apples and oranges, right? But this the reality is more nuanced because we have an interaction of two matrices. We have A and we also have double channel mixing. And it's the interaction of the eigenvalues that determines whether you will have oversmoothing or not. Right? So that's what when I say interpretability, I mean this, right? So we'll be able to prove these kind of results. Now, this is an example of how it works in practice. So here we have a node classification task on synthetic core, so we can artificially control the level of homophilia in the graph. And here the two extremes would be to use classical graph convolution architecture like GCN. So it works very well when the graph is homophilic, but it works poorly when the graph is heterophilic. And the other extreme is to ignore the graph altogether and to use node bicycle, right? Which works with the same accuracy independently of the level of homophilia. So with the gradient flow approach, we can benefit from the homophilia of the graph when the graph is homophilic, but then we deteriorate nicely in the performance and we perform on power with the node bicycle. Right? So you continuously gracefully switch between these different regimes, the homophilic and the heterophilic. Now, if we look at how this homophilia assumption comes across in images, right? So if we try to look at the diffusion equation on the grid, it corresponds to this homogeneous diffusion equation, right? So by homogeneous, I mean that the way that the diffusion works at every position is constant, right? So the diffusivity function appears here. That's the constant C. So if I take an image, for example, this portrait of Newton, and I apply this kind of equation to it, this is what I get. So I actually have a closed form solution. I can write it as convolution with the Gaussian, where the sigma, the variance of the Gaussian, will be increasing with time, right? And in the limit, the Gaussian will be very wide, right? And I will just get the average color. T goes to now, if you look at the kernel of this equation, right, the heat kernel, it will be a isotropic filter. It's obviously undesirable because I completely destroyed all the visually important information in this image. So the idea that appeared in the 90s, in the seminal work of Perron and Malik, that actually incorrectly called it an isotropic diffusion, so it's isotropic but non-homogeneous, is to locally control the speed of diffusion by a function that is proportional, inversely proportional to the gradient of the image, right? So it's an indication of discontinuity or edge, right? So what I want to do is I want to avoid mixing pixels of different color. So I don't want to mix together white and dark pixels, right? Because that's exactly what creates this blur effect. So basically, I want when I in the dark region and I'm moving to the white region, I want to slow down or potentially stop the diffusion. So the kernel of this nonlinear diffusion will look like this. And this creates much nicer images. And there was an entire field of variation on PD-based image processing and computer vision. It's very mathematically, aesthetically appealing, right? You can say that I have an energy that the functional that tells me how my ideal image looks like. I can derive Euler-Lagrange equations, conditions in the evolution equation, and run it on the image, and I get the desired image. So all these methods were, I think, fair to say, wiped completely by deep learning. And the reason, of course, like everything else, it's very difficult to handcraft the functional an evolution equation that would fit any kind of data. Right? So with in the deep learning era, we can actually make these equations parametric. And if you think of this kind of nonlinear diffusion, that's exactly what we see in attention. Right? So that's the idea of attention, but done 25 years before. Right? And basically, nonlinear filters like bilateral filters or non-local means or similar ones were basically re-implemented with learnable edge. So this is how the non-homogeneous diffusion will look on graphs, right? So we have here again the gradient. This will be the learnable diffusivity, right? Implemented as an attention. And if we discretize this equation with explicit Euler discretization, right, forward Euler scheme, and we make some assumptions about the time step and the normalization of this diffusivity, we get the classical graph attention. So you can see that attentional architectures can be considered as a special case, special way of discretizing this diffusion equation. Now, I remind you that we wanted a continuous model of convolutional graph neural network architectures. What we've seen so far is only continuous model for time, right? Which is, you can argue, not such a big deal, right? So it has been already done, for example, with neural ODs. And again, I remind you, if we want to discretize the diffusion equation in the plane, I don't have a unique way of discretizing the spatial Laplacian. So these are three different discretization of the Laplacian, and any convex combination, because of the linearity, is also a valid discretization. Right? So what I'm trying to say here is that you don't have a canonical computational graph when you try to solve diffusion equations on the grids. And we can again take analogy from what has been done in image processing now by considering not nonlinear diffusion but non-Euclidean diffusion. And what I mean by this is the following model, where we consider the image as a manifold that is embedded in a joint space that has positional coordinates of the pixels and their feature coordinates. Right? So if you have a color image, you can think of it as a two-dimensional surface in five-dimensional space. Right? Every pixel has x, y, r, g, and b coordinates. Right? So the x, y will be the positional coordinates, and r, g, and b will be the feature coordinates. Right? And basically, this is a manifold. By virtue of this embedding, we can define the Riemannian metric, special one, called the Pullback metric. And with respect to this metric, we can define a non-Euclidean version of the Laplacian operator that in differential geometry is called the Laplacian Beltrami operator. And this diffusion equation is called the Beltrami flow, and it's also a gradient flow of an energy that is called the Polякov functional. It's a generalization of the initial energy, and it's used in string theory, bosonic strings. So we can do the same thing on a graph. So now every node comes with positional coordinates and feature coordinates. They're coupled through this learnable diffusivity function, right? Attention. And now the evolution of the feature coordinates is the standard feature diffusion. But the evolution of the positional coordinate, you can think of it as a kind of soft graph divider, right? So if you have two nodes and they come close in the positional space, then I can decide to introduce an edge between them, so to facilitate the flow of information. And conversely, if they drift apart, I can decide to cut the edge so I don't flood my graph with unnecessary information. So I know that it might be not very easy explanation, but this is how it looks. This is again an example of Quora. So here we have again low example of graph. So the colors represent some low-dimensional projection of features, right? They call it the RGB colors. The positions of the circles will be the positional coordinates in two-dimensional projection, and we are trying to do here node classification. So the evolution pulls these clusters apart, so both the positional and the feature coordinates evolve, but also the graph is changing. This is a kind of disturbing picture because if you think of it from the perspective of signal processing, we have a situation when we are filtering a signal on the domain, but the domain is also changing at the same time, right? So it might be not the usual picture in signal processing, but it's actually a very usual picture in differential geometry. And in differential geometry, it's very common to take a manifold and subject it to some evolution equation that might actually structurally look like very much like the diffusion. So famous class of such evolution equations are Ricci flows. So if you look at it, what is shown here, so G is the Riemannian metric, right? Locally, it's an inner product of the tangent space of the manifold that allows you to measure distances and angles. So it's temporal derivative, right? Like in the diffusion equation. The right-hand side is what is called the Ricci curvature tensor. So it's also second-order differential quantity similar to the Laplacian. So bottom line, what it does to this manifold that is shaped like a dumbbell, so it has positive curvature here and negative curvature here. It rather the evolution equation by Ricci flow, it becomes more like an ellipsoid and then like a sphere, and then collapses into a point. And Ricci flows were introduced by Richard Hamilton with the purpose of proving the Poincare conjecture. So Poincare conjecture posits that you can characterize topological spheres by the ability of to take any closed curve and collapse it into a point. Right? So if you think of, you can always do it on a sphere, you cannot do it on a torus. Right? So two-dimensional example, if this is a torus, so this is my closed curve, I cannot collapse it if it leaves across the donut, right? So if it leaves along the donut like this, then I can always collapse, right? But on a sphere, this is always possible, and the conjecture was that it works also in 3 dimensions. And as you probably know, it was topologies were involved when about 20 years ago, Perelman differential geometry proved the equilibrium conjecture with differential geometric tools. Now, what does it also have to do with graph neural networks? Remember this problem of oversquashing, the failure of message passing to propagate information on the graph. So this happens when we have two phenomena that happen at the same time. So when we have a graph that has fast volume growth, right? So things like trees or small world networks, when you look at the number of neighbors of the neighbors of the neighbors, it increases exponentially. Right? So it means that I have a lot of neighbors from whose features I need to propagate. And if my task requires to send information between distant nodes, then basically I have a lot of information I need to squeeze into a single feature. Right? So you see that this is a combination of two phenomena. So it's something that has to do with the structure of the graph, right, with topology, and something that has to do with the task. Right? So let's first look at the graph topology. And the way that we can mathematically characterize this phenomenon of oversquashing is through some form of sensitivity analysis. So if I give you a multi-layer message passing neural network with some assumptions about the architecture, what I can do is to ask, if I look at the output of the neural network at some layer L at node I, what happens if I perturb the input to the neural network at some distant node J, right? And this perturbation will be propagated by the neural network, and eventually I will see its effect at the output. But whether this effect will be strong or not will determine whether I have oversquashing. I can measure it by looking at the partial derivative of the Jacobian, right? And if the norm of the Jacobian is small, it means that information is somehow lost on the way to the output, right? So small Jacobian means that I have oversquashing. What we show in our paper that we can bound the norm of the Jacobian by some set of parameters that depend on the architecture of the message passing neural network, as well as the topology of the graph, right? So it comes here across for some power of the normalized adjacency features. Now, what you typically can change is this, right? All the green parameters. So I can add more layers. I can increase the number of neurons. I can change my activation functions. I typically cannot change this, right? So this is part of my input. This is the graph that I want to do, unless I can allow the graph to be different, right? So if I decouple the computational graph from the input graph and do what we call graph rewiring, I can also change the radical. Now, if we look closely at how the topology influences the phenomenon of oversquashing, we intuitively expect that something like this, like a grid, will probably be less prone to oversquashing than something where the volume grows very fast, like a tree, right, or a small graph. So we need something more nuanced than just the adjacency matrix in order to analyze this phenomenon. And this is exactly where Ricci curvature comes into play. So I remind you that in differential geometry on manifolds, the way that you can think of curvature is by what we call geodesic dispersion. So I have two nearby points. I send geodesics from them in parallel. And if the geodesics remain parallel, then we have Euclidean geometry. Right? So it's, the space is flat. If the geodesics converge, then locally I look like a sphere, and if they diverge, locally I look like a hyperbolic space. So we can define something like this on graphs as well. So there are several notions of discrete Ricci curvature on graphs, but roughly what you can do is to take two nodes connected by an edge, let's call it P and Q, and I can shoot edges, right? So I look at edges that emanate from these nodes, and if they tend to form triangles, then I locally look at something that looks like a click. If they form rectangles, then this looks like a creep, and if they drift apart, then it looks like a tree. And we can measure, basically, we can give it a number, so it will be defined for every edge in the graph, and we call this balanced forward curvature. So it's a discrete version of each curvature on the graph. It's positive for clicks, 0 for grids, and negative for trees. And the main result in the paper is that we can attribute over squashing to the presence of strong negatively curved edges. And once we know it, we can do something similar to Ricci flow, so we can evolve the connectivity of the graph by removing the edges with strong negative curvature and replacing the edges with high curvature. And we show that it allows to, without touching the graph significantly, improve the performance of graph monomorphs, both in homophilic and heterophilic settings. Now, what is the problem with this approach? It completely ignores the task, right? So it only analyzes the topology of the graph. And why task is important? Because I can give you the same graph, right? And the same features, but the task that I'm computing on this graph will be different, and whether the graph is suitable for this task or not for message passing will depend on the task. Right? So here's an example from chemistry. So the graph here represents a molecule, right? So we have atoms connected by chemical bonds, and I would like to ask whether using this graph is good or not. Right? So again, it depends on the task. So the kind of functions we would like compute in chemistry, different types of forces or different types of interactions. So one type of forces that exist in molecules is what is called van der Waals interactions. They decay very fast, like 1 over r to the power of 12. Another type of interactions are what is called electrostatic or colonic interactions. They decay slowly, it's 1 over r, right? So in this case, probably this local graph will be suitable for message passing, and in this case, it would not. Right? So here, maybe I need to account for interactions between all the atoms in the molecule. So again, this is an example where I have the same graph, the same features, different task, and for one task, the graph is not good, and for other, the graph is good. So this brings me to the last figure that I wanted to discuss is basically how the task affects oversquashing, right? And basically what's the interplay between the structure of the graph, the neural network architecture, and the function that we want to compute. So first of all, what I mean by task, the task is a function on the node features of the graph. So here's an example. So I get some information from the node features and compute some function. So the way that nodes interact, we can capture it through what we call the mixing coefficient. So this is just some bound on the mixed second order derivative, what is called Hessian. And you can see in the simplest case, if we have completely separable function, in this case, the second order derivative will be 0. So in this case, the nodes act on their own, so they don't interact at all, right? So they don't mix. Another extreme example, when we have a function of the inner products of the features, in this case, all the nodes interact with each other, and the mixing will depend on how linear this function finds. Right? So this is again maybe very simplistic, but that's a way of characterization of interaction between the nodes. And now we're interested in this kind of capacity bounds, right? So we can ask questions: what is the capacity of MPNN required for a given task? And the capacity of MPNN, it depends on the model and the topology, right? Because I remind you, topology tells me how I send information in my MPNN, but the task is characterized by mixing, and we have this inequality that means all of it. And I can provide bounds, for example, on the weight of the neural network or on the minimum depth of the neural network. Right? So I can say that I need a certain number of layers in order to solve tasks with certain mixing on a graph with certain topology in an MPNN architecture with certain parameters. Right? And for example, we can show that depth must be proportional to the commute time, right? So the time that it takes to random walker to get from one node to another back in expectation. And different rewiring techniques, including the curvature-based, but also other things based, for example, on expanders, they try to improve the commute time. In fact, I think for commute time, for expanders, the commute time is linear. But in the worst case, it can be cubic in the number of nodes. Right? And this allows us to write a characterization of the expressive power that doesn't resort to the Weisfeiler-Lehman formalism. So it is more general because here we don't necessarily assume that the graph is the same, right? So the input graph can depart from it. And the expressive power can be characterized in the form of impossibility statements, right? Let's say that a message passing architecture with certain number of layers cannot learn tasks that require certain mixing between features that nodes separated by certain code. So I think it's about time to move away from Weisfeiler-Lehman and its expressive power in different ways. So the very last thing that I would like to mention in the last 5 minutes is if we again look at what we've seen so far, right? So we talked about different ways of sending and aggregating information, right? So you can say roughly what kind of information you are sending, right? When we talked about the graph rewiring, we also said where this information is sent, right? So do I send information just from my neighbors, or maybe I select a subset of them, or maybe I introduce new connections, right? So I can connect to more distant nodes, right? So this answers the question of where to send information. But remember, our metaphor was of a dynamic system. So the last piece that is missing is when to introduce this information. And let's look at this example. So in a classical message passing architecture, if I want to send information from the red node to the green node, it requires 3 steps, right? So first the information goes to the neighbor, then to the neighbors of the neighbor, and then it arrives at the green, right? So 3 layers are required to get the feature from Q to V. In a transformer, this happens in 1 step, right? Because the graph is fully connected, so every node has access to every other node, of course, at the expense of computational complexity, right? So it's cubic, it's quadratic, and also at the expense of the phenomenon of squashing, right? So I can overwhelm myself with features that I don't necessarily need. Right? So what we can do, we can do what we call dynamic rewiring, so we can gradually introduce this extra information. Basically, we know that in message passing, the information from the red node will arrive at this node after 1 layer. So let's create a connection there. And what we can also do, we can introduce this information with delay. So this will be some kind of sparse skew connection. So I know that information from the red node will appear at the green node after 3 steps, but it will be somehow mixed with the information of the neighbors. So let's introduce it directly. And we call this dynamic rewiring with delay, or NDRIV, and it used to be state-of-the-art architecture for long-range interaction benchmark, not anymore, but I think it's an interesting approach. It would be interesting also to analyze its expressive power. It's more general than just this. So the last thing we can also do in any type of rewiring, right, or any type of message passing, every node both sends and receives information, right? So no matter how I rewire the graph, whether I do it dynamically, whether I do it statically, the node has these both functions, right? So I aggregate information from my neighbor, but I also transmit information to my neighbors, and this makes the message passing synchronous, right? So I need to wait for all the messages to run, which is not necessarily a good idea, especially when the graph is very large, and maybe it sits in different parts of the memory, right? And some messages take significantly more time to be sent. What we would like to do is to do local node level control. Each node can decide what it does, whether it wants to send messages or only to receive messages or to do nothing. And we have these 4 different options. A node can broadcast and listen. So like in standard message passing, it can only listen, it can only broadcast, or it can isolate. This was actually an image that took several days to generate with valid feeds. People complain that will be killed by artificial intelligence. I think we're still far from it, judging by these examples. And basically what this architecture creates, we call it cooperative message passing. It's kind of dynamic rewiring that is task specific, so it's done on the fly. It is stochastic because we need to sample from the action space, right? Every node a special neural network that is trained to decide on the actions. It is more powerful than WL in expectation. It's not equivariant. It's similar to random node features. It avoids oversmoothing. It avoids oversquashing. It is asynchronous, so it has a bunch of nice properties. And well, of course, I'm biased because it's our paper, but I like this work because I can think what else can you do with message passing, right? It seems like everything has been invented already, but I think that this is a new and fresh look. So I know that I'm at time, so let me summarize. I think this physical viewpoint offers a new perspective on all problems like over smoothing, over squashing bottlenecks. It allows to explain old architectures, but also it allows to derive new ones, and probably more importantly, in existing architectures like convolutional architectures, which is a very vast category, it allows to make principled architectural choices. Right? For example, whether you use a residual connection, whether you share weights across layers, whether you make them symmetric. You can provide theoretical guarantees, right, about stability, convergence, expressing power. And I didn't show it, but we can also do more exotic types of diffusion on cellular sheaves, for example. So it brings tools from fields that are maybe less popular in the knowledge, like algebraic topology and differential geometry. And I think there is a lot still to be done in this field. So I hope that I convinced you that it's a worthwhile direction. So I will stop here. Thank you very much for listening.
We will have I think enough time for questions. So we'll have a mini action social event here. If you have questions or interactions, feel free to grab food and but right now let's have a few like follow-up questions.
If you use implicit method rather than explicit method, how would it change the over squashing problem?
So implicit methods mean that you don't have basically you don't have message passing, right? So it means that your propagation operation is dense, and basically you access not only your immediate neighbors, right? So eventually it avoids over squashing in a similar way that we do with delayed message passing. So you have access to distant nodes. We haven't analyzed it. I think you can try to do so. The way that we look at the behavior of deviation energy. So we have something along that direction. So that was probably more from the perspective of generalization. What happens when you perturb your graph? So model that generates graphs and you change the distribution of the connectivity. So it was an advective diffusion problem. So it has both local message passing architecture, global transformer-like architectures. It's not exactly implicit, but it's similar. Maybe it is also a philosophical question, and this is where I disagree with Peter, whether everything should be considered message passing. Right? So I think actually diffusion equations are a good example. So in the diffusion equation, I can give you a closed form solution to diffusion at any time, right? Infinity. Do I really need to do these message passing steps on the graph? Right? I can give you everything at once, right? So the information is exchanged at once in the form of the heat operator. So at least in the strict sense, it's not message passing. What we show, so we have a recent paper. So this is a continuation of this idea of shift diffusion. So shift basically what it does, it's a discrete analogy of parallel transport, right? So when you write your derivatives, you can only manifold. You cannot just subtract your features at 2 points, right? So you need to transform your feature vector when you bring it from 1 point to another. So the analogy would be to have an operator that lives on the edge of the graph, right? And then when you compute the derivative, right, the gradient, it acts on the neighbor feature. And you can restrict it to some subgroup of the general linear group, right? Like rotation matrices. So long story short, if you assume that this sheaf is flat, you can replace the edge-wise operators with node-wise operators. So basically what you do synchronization. So you first rotate your node-wise features in a learnable way. Then you solve the diffusion. Basically you run it asymptotically to infinity. So you have a closed form solution to it. You can use some series, rational or Taylor to do it, right? So, and then you do desynchronization. So there is no message passing. So the interaction between nodes happens through this learnable synchronization. So again, I think message passing is a limiting concept that we need to move beyond it to design new graph.
Thanks, Michael. So I'm coming from finite element meshing and physics simulations. So can you comment if you want to extend this to three-dimensional with 3D topologies? Another thing is we are worried about a lot of these chaotic systems. where like turbulence and cavitation. So can you comment some of those ideas can be explored or not?
So I know less about the turbulence and coding things, but it's actually a very interesting question, and I think also it's shows some kind of philosophically very different approach. So all this stuff, for example, we've been doing it for ages in geometric processing, right? So the idea of doing filters on meshes, I think it has been done at least in the early 90s. So Gabriel Calvin, for example. Now, so in a sense, it has been reinvented in graph networks instead of a mesh graph, right? So more or less everything is the same. Now, the key difference, in my opinion, which is probably more philosophical, and I wonder why this is not the mindset in graph ML community, is the following. So when you want to do some kind of computation on the mesh, so the mesh is a nuisance, right? So you don't consider it as a kind of sacrosanct object. So you assume that the mesh discretizes some continuous object, and you want to be invariant, or at least insensitive to the way that you discretize, right? So I want my function to be the same no matter how I change the mesh. And you can guarantee it in certain ways. On graphs, on the other hand, I somehow fanatically trust that the graph contains important information, and I don't allow it to change. So what can be done, for example, so we had a paper which with Justin Solomon from MIT, where we looked at what kind of functions you can do on meshes when you assume triangulation invariance. So again, long story short, the way that you can represent it is in the form of functional map. So it's a map between spaces of functions that live on meshes, and under some technical constraints like volume preservation, you can describe it as orthogonal map. So orthogonal map is a generalization of permutation. Permutations are orthogonal. So instead of permutation invariance, you have invariance under orthogonal maps. We characterize the class of functions. So the conclusion is that if you represent your mesh as an operator, then the functions that you can learn under these conditions are only functions of eigenvalues and eigenvectors. But the operator itself can be loaded. So I think this mindset of replacing the graph with an operator that is defined on a graph is very healthy. And I haven't seen it done in graph neural networks. So there are some initial works that tried to do it. Was in the summer there was an architecture from my collaborator at Oxford called GRID. So they had this idea of propagation operators, which is a little bit similar. But I haven't seen it applied at all. And regarding the numerical phenomena, I don't know. So usually you have some physical constraints, some extra constraints like conservation, momentum, etc. that you build into your dispensation. So your operators satisfy this by construction.
I think very aesthetic talk. I would like to ask a similar question, but in the opposite direction. From the work on sheaves and, let's say, some visual objects, do you think there might be novel insights on how to solve intrinsically combinatorial problems with learning features that are meaningful to transport information across things that classically are combinatorial?
You mean something like integer program, right? What is that?
That would be a very classical example. Yes.
So that was the hope. Well, I'm not an expert in this. This is what Peter, for example, is working on. So the hope was that basically with trying to relax these problems with graph neural networks, you will learn some heuristics. You will be able to explain some heuristics that are known and handcrafted. I haven't seen this yet. Again, maybe it's not a breakthrough. I know, for example, that these approaches do not generalize to graphs of different sizes. So if you like traveling salesman problem of size n, right, and you learn to solve it with some graph neural network, then you would apply this network to n+1, and it doesn't degrade significantly. Something like that. Maybe that has some recent progress that I not aware
Thanks for the talk. I have a question from the perspective of generative models. So you mentioned the importance of symmetry principle and network expressive power. Can we leverage these two tools to benefit the design of generative models?
So in generative models, well, of course, it depends on exactly what you're trying to do. But let's say in molecules, the score functions are usually implemented as equivariant GNNs. So there you want to make sure that the probability of a certain configuration is invariant with respect to to some growth transformation, right? So roughly, if I have a molecule and no matter how I rotate it, it should be equipotent, right? So that's what the state these architectures.
Yeah, yeah, thanks for that. For the other part, we have, for example, a Weisfeiler-Lehman test for GN architecture. Do you think we have a counterpart for generative models? For example, some kind of architecture cannot generate kind of something like that.
So I think the short answer, at least to my knowledge, no. We're looking into it. So I have a new postdoc she comes from Canada, from Milan. He's looking into trying to characterize the generalization power of generative models. I don't have any results yet.
Thank you.
Hi, Professor Bronstein. Thanks for the experiment. So I'm curious about the potential application of geometric deep learning into image generative models. So let's say we want to train a diffusion model of pizzas. We have pizzas on the table and we take photos of them from the top-down view. And so in this case, we probably want the model to be able to generate pizzas up to any rotation, right? But if we want to train a diffusion model that also, besides generating pizzas, also wants to generate the Eiffel Tower, we probably don't want the model to generate an upside down Eiffel Tower. So do you think in terms of images, the symmetric property of images should be deferred? Like, is there a principled solution to treat different images?
I don't know. I'm not sure that in generative cases that's the case. So in general, groups are only a simplistic abstraction of transformations that images can do. So the general transformations of objects is more general, so it doesn't necessarily form a group. You still what you get in, for example, in convolutional neural networks, that the property that we call geometric stability. So if you're absolutely far from a group, then your invariance or equivariance holds all the effects on it. I'm not sure that this is something that can be guaranteed in geometric models.
So you had this sort of dynamical system that's meant to describe the node features in this given graph, like there was some graphic of that evolving over time. Can this framework be adapted to also dealing with edge features, and as an extension to that, when you're doing rewiring, like where you're having edges show up and go away based on some closeness or some additional closeness between nodes, how would that be able to adapt to edge features? Like, would you need a different sort of dynamical system, or one's running in parallel?
Well, it depends on what kind of features, right? So you will probably need to encode them in some way. So it depends whether these are categorical, continuous features. We haven't done much with it. So on sheaves, you can encode, of course, the edge features. They also have some geometric space. So that will be pretty straightforward, right? So maps from the node space to the edge space. That will be addressed. And then basically it is hidden in your diffusion operation. Basically the analogy of the loss regarding
Okay, let's set our speaker again.